Alright, so today we're going to be talking about real gases and the deviation from the ideal gas. So, if you remember, ideal gases can be represented mathematically with, I don't know, my pen's doing that, PV equals nRT. And this formula is great because it's actually pretty accurate depending on what you're calculating. But it makes two assumptions. So, number one, it assumes that the gas has no intermolecular force. Or forces. Which we know is not true, but for the purpose of doing this calculation, this assumption really doesn't change most calculations too much. I want to fix that. So the second assumption is that the molecules in the gas, or molecules of gas, have no volume. Which, while their volume may be negligible, each individual molecule does technically have a volume. So you can pretty much assume that it doesn't under most circumstances, but there are cases where you have like extreme temperatures or pressures where these wouldn't make sense because of the conditions that the gas is in. So that's when we would use the van der Waals equation, which looks very similar to the ideal gas law, but it takes into account two different properties. So I'm going to write so you have P plus AN squared over V squared times V minus NB equals nRT. So if you look at the ideal gas law, you have PV equals nRT. P times V equals nRT. So you're just really adding in these two things right here. And right here. The pretty much minus NB. So what does that mean exactly? So V minus NB is volume of container minus moles and then times volume of gas. So what it's taking into account is that each molecule has volume. So you have the moles of the gas times that property. It's going to be a value provided to you. And then you have P plus AN squared over V squared. And that comes to pressure plus, and then we're going to need a separate set of parentheses. So actually, let me put this in brackets. So you have pressure times molecular attraction times moles squared. So you have times moles squared, and then this whole thing is divided by volume squared. So nRT, same thing as the other one, moles times gas constant times temperature. Everything's got to be in standard values. Really what you're doing is you're adding in two tabulated values to calculate the difference between the ideal gas law and this. It's just going to give you a more precise answer. So, did I write everything? Oh, so for A, let me see, did I write that? No, I didn't. So A is the degree of attraction. So you have degree of attraction depending on the gas. And then B is volume of molecules depending on the gas. Alright, so what I'm going to do is we're going to do probably 1 or 2 practice problems depending on how long this is going to take. So let me go down, and we're just going to work on it on this page. If you need to copy the other stuff, just go back up and pause the video. So, alright. Carbon dioxide gas, 1 mole of it at 373 kelvins, occupies 536 milliliters at 50 atmospheres of 50 atmospheres. So what this question is saying is we're going to be calculating the deviation, which is pretty much the difference between this number and what these two equations spit out in terms of values. So one thing to be aware of is if you see something like this, you have this much pressure in that small amount of, volume, it's probably going to be more accurate to use the van der Waals equation. Reason being is that's about a quarter of the volume of a 2-liter bottle of soda. So you figure you're putting 50 atmospheres worth of pressure in that. It's going to have a lot of, almost no volume in there. For that much pressure, it's crazy. Anyways, just like a little sidebar thing. So the reason you would use this formula in industry, I don't know if I said this or not, but I'm going to repeat myself. So say you were a manufacturer or something and you're building a tank to help produce something and you're containing gas. Maybe it doesn't matter if it's really toxic or not, because anything under pressure is dangerous. But you need to be able to calculate how much pressure, what the tank can withstand because the engineers built it. But you need to be able to calculate what the pressure of the gas is inside of it based on what you have in there. And while you could use the ideal gas law, it's probably not accurate enough to give you a real, comfort in that the tank's not going to blow up on you and, hurt a bunch of people or, cause delay in production. These are all things that are thought about that we never really think about. But they're necessary because, safety is, important in any manufacturing or, engineering job. It's just safety is, the utmost importance. So with that real world scenario, you can kind of see why this equation would be so important. And I'm going to show you just this small little problem right here where it's not that much gas, because 1 mole of carbon dioxide is 44 grams or something like that. It's not really that big of a value. 44 grams is nothing. But at that pressure, that's a lot of pressure for that small volume. So anyways, first we're going to calculate the deviation, which would just be, Yeah, actual minus theoretical, the absolute value, divided by theoretical times 100%. You've seen that formula before, countless times. It's how you calculate percent error. So this is percent deviation. Same thing as percent error. Alright, so we're going to do ideal gas first so we can see. Alright, so we have one conversion to do because it's got to be in liters. So we have 536 milliliters times 1 liter over 1,000 milliliters. And that's going to be equal to 0.536 liters. Alright, all of our conversions are done. And we're going to just plug this in and see what we get. So we have N equals 1 mole, T equals 373 kelvins, and we know P is equal to 50 atmospheres. It's an ugly 5. Alright, so let's calculate and compare against what we know. So we have P equals nRT over V, which is P equals 1 mole times 0.0821 liters times atmospheres over moles times Kelvin times 373 kelvins divided by the whole thing. Divided by 0.536 liters. So we have 1 mole times 0.0821 times 373 divided by 0.536. And then this is going to give us an answer of about 57.3 atmospheres. So P equals 57.13, or 0.1, it doesn't matter. So this is a little higher than that. I mean, it's still close, but 7 atmospheres is quite a big deviation. So let's calculate how much it was off by percentage-wise. Because, 7 atmospheres could be make it or break it for, a real-world application, whereas it's got to be, pretty precise. So, percent deviation equals absolute value of 57.13 minus 50 divided by 50 times 100. So if you get a negative number, just know it's not negative. You're not going to have a negative percentage, but so this is going to give us about 14.26% deviation. So from the looks of it, that's off by quite a bit. Now let's compare it with using the Waals equation. So we need to, I'm going to copy these so I don't have to rewrite them. Okay, so we have P plus AN squared over V squared times V minus NB equals nRT. It's quite a lot of stuff, but we already know N is equal to 1 mole, T is equal to 373 Kelvin, R is the gas constant. I'm not writing all this stuff. Actually, let me just write it. This is going to bother me if I don't. And then volume is 0.536 liters. Okay, so how you're going to solve this is you can do it algebraically or not, doesn't really matter. You're going to get the same answer. I just like plugging numbers in just because it's easier for me to see it that way. But you can do it any way you want. So let's start. We have P plus A, which is 3.61 liters squared atmospheres over moles squared times 1.00 mole squared over 0.536 liters squared. So you see something that's canceled, and 1 squared is just 1. So this would be the first value, is all this, times, and then we have 0.536 liters minus 0.0428 liters over moles. So just like a quick little sidebar, if you ever see a negative exponent like right here or right here, what that means is you have that value on the bottom, like in your denominator. That's all it means. So, and then this is equal to nRT. So, let's start doing some algebra. So, now that we have our units, we have atmospheres, because this is going to eventually cancel. So we get liters, but I'm not going to do that now. Alright, so we have P plus 3.61 times 1 squared over 0.536 squared. And then I'm going to put this in brackets. And then that's times 0.536 minus 0.0428. And then that's equal to nRT, which is 1 times 0.0821 times 373. Not writing the units out simply to save room, but they will be canceling. Alright, and the liters would cancel over here when you divide it out. So I'm going to need more room, so let me copy this and go to the next page. If you need to pause and copy it, go for it. Okay, so we have pressure plus all this, so that means we have P plus, let me do this in the calculator, 3.61 times 1, and that's divided by 0.536 squared. So we have 12.57. 12.57 times, so we have 0.536 minus 0.0428. And then that's 0.4932. And that's equal to 1 times 0.0821 times 373. So we have pressure. This is N squared over V squared. This is V minus NB. And then this is nRT. So let's do some algebra. So we have 0.4932 P plus, and then I don't know what that is, so that's 12.57 times this number is 6. We'll do 6.20. 6.20 equals, and then we have to figure out what that is. 1 times 0.0821 times 373. And then that's going to be 30.62. Okay. And then I'm going to do so that's mole cancels, temperature cancels, and then we have, let me just do it because otherwise I'm going to get confused. So we have liters, time, atmosphere. And then this is going to be liters. Anyways, so yeah. So we have 0.4932p is equal to, don't worry about this because it's going to drive me nuts. Probably should have canceled it long ago, but it does cancel, so don't worry about it. So we have 24.42. So 24.42. And then this is how we're going to figure out what our pressure is. We divide out 0.4932. 0.4932. And then this is going to be equal to P. Let's do it in the calculator. So that's going to give us a pressure of about 49.51 atmospheres. So this was with the van der Waals equation, which compared with 57.1, that's quite a big difference. So let's compare this to the 50 atmospheres we were given. Absolute value of 49.51 minus 50 divided by 50, and then that's going to be negative 0.49, so that's just going to be 0.49 divided by 50 times 100, so it should be about a little less than 1%. And then times 100. So the deviation is 0.98%. That's nothing. So as you can see, the actual van der Waals equation is much more precise. That's why it would be used in place of the ideal gas law. So I have one more problem that we're going to do if we have time, because I don't want to make this too long. Yeah, we have time. So let me... Did I erase it? Oh. Let me find it on the... Thought I had it in here. Nope. Here, let me... Real gas. I found one online that I wanted to show you guys. Where was it? Was it this one? Might have been this one. Yeah, it was this one. Alright, so we're going to go to a new page. Alright, so the problem says 1 mole of ammonia fills a 7-liter bottle at 350 kelvins. What does the van der Waals equation predict that the pressure will be for the ammonia? So I'm going to show you a different way of doing this. So we have N equals 1. So we have 1 mole, V equals 7 liters, and T equals 350 kelvins. So let me open my water. So anyways, A is going to be 4.17 liters squared times atmospheres over moles squared. And B is going to be 0.0371 liters divided by moles. So I'm going to do this first with the ideal gas law. PV equals nRT. So very simple. P equals 1 times 0.0821 times, and I know this is bad form, but at this point you guys should know what cancels if you're going for a certain thing. Just trying to hurry up so this video is not forever. So your answer would be pressure of about 4 atmospheres. Pretty good. 4.1, whatever. It's close enough. So I'm going to write that down. Alright, so van der Waals equation. P plus n squared over v squared times v minus nb equals nRT. So let's do, you have, you could also just solve this the easy way. Divide out v minus nb, v minus nb, and then you have p plus n squared over v squared equals nRT over v minus nb. So then you can subtract out n squared over v squared, and then on this side you have minus an squared over v squared. So P, let me move this over so I can rewrite it. P is equal to nRT over v minus nb minus n squared over v squared. So now we're going to calculate this. I'm going to copy, I'm going to write all the values and then just copy and paste them down. So let's move these over here. And then A equals 4.17 liters squared atmospheres over mole squared. And B equals 0.0371 liters over mole. Okay, perfect. So we're going to copy this. And go down here. Okay. So P equals 1 mole times 0.0821 liters times atmospheres over mole times Kelvin times 350 Kelvin. And then that's divided by, we have 7 liters minus 0.0371 liters over mole. So, and then this is minus, where is it? 4.17 times 1 mole squared divided by 7 liters squared. Alright, so this is a lot to kind of write out. Pretty much what you need to know is all your stuff's going to cancel. So all this stuff is going to cancel. And you're going to be left with atmospheres. So now all that's left to do is plug this into the equation. So you have 1 time, that's a great start, 1 times 0.0821 times 350, close that, so that's the top one divided by, open another set, 7 minus 0.0371. And then that is going to be minus, you have 4.17 times 1 divided by 7 squared. Close that, and you should be done. And then we're going to get an answer of about 4.0441 atmospheres. So as you see, you can do it this way or you can do it the other way. I did it where I left it. You have P plus, and we'll see what we get. P plus, I'm going to just write the numbers, 4.17 times 1 squared over 7 squared times 7 minus 0.0371 equals 1 times 0.0821 times, I'm doing it this way so you can see the math, in real action. It's the same exact equation. It should give the same answer unless there's an error with the calculator. So anyways, you have 4.17 times 1 divided by 49, so that's 7 squared. So that's going to be 0.0851. And then that's P plus this. So that's times 7 minus 0.0371. And then that's 6.996. Yeah. 6.96 equals whatever that is. 1 times 0.0821 times 350. 1 times 0.0821 times 350. That's going to be 28.735. Alright, so first thing you should do is FOIL this out. So you have 6.96 P plus whatever that is. Or you could divide it out. It doesn't really matter. I'm just showing you the way I did it the first time. And that's going to be plus 0.59. 592. So you subtract 0.592. And then you have 343.28. And you divide it by 6.96. So we have 28.343 divided by 6.96. And it's a little off because I did some rounding, but it's about the same number. The reason I got 4.04 is because in the original equation there was no rounding that happened, but as you can see it gives the same answer. So now let's take the deviation based off of the ideal gas in this one, and it's going to be a little closer than the other one because it's not as extreme. So we had 4.1 atmospheres minus, well, we're going to see the difference, 4.04 because that's the divided by, I don't know if it gave us one. Yeah, we're just going to use, we can't even do this because we don't have a theoretical value. So you don't have to worry about it, but you could see that the van der Waals is going to give a little bit of a more precise answer based off the first one. But if I say that it was 4 atmospheres, I'm just guessing, was what it was at, and you had 4.1, you would do absolute value of 4.1 minus 4 divided by 4, and that's going to be 0.1 divided by 4 times 100. It's going to be like 2.5%. whereas you have 4.04 minus 4 over 4 times 100. You have 0.04 divided by 4 times 100, and then that's going to be 1%. So it's a lot more accurate / precise to use the van der Waals equation. I know they don't look hard, they don't look easy, but they really are if you just take the time to set the problem up correctly. If you have any questions, make sure you go to my office hours, as I'm sure many of you are going to. And that's it for this video.